Hello everyone, I'm Greg Weaver. Welcome to the Audio Analyst. Pardon me. Before we delve into today's discussion about amplification, I'd like to take just a moment to thank all my subscribers for their gracious and kind comments and the overwhelming support of my work here on the channel. If you find any merit or value in these conversations, if you enjoy the information I'm sharing here, maybe today is the day you'll finally click that subscription button. Feel free to click like on any episodes you enjoy and to share links to your favorite episodes with your friends. And don't forget to leave your comments for any episode. I try to respond to them all. And should you feel you might wish to really help support my efforts here, and in the process receive exclusive access and content, then please consider becoming a patron by using any of the links in the comments section below this video. I've set a wide range of Patreon subscription levels. Or, if a one-time donation makes more sense for you, I've provided PayPal and Venmo account information as well. Believe me, your support at any level enables me to continue producing these videos and is sincerely appreciated. Now, one category of question I get asked about quite frequently has to do with the differing types of amplifiers. It seems many music lovers don't have much understanding about their types and classifications, often asking which type of amplifier is best. Well, like most subjects, there is no one answer. So today, I want to cover some basic about amplifiers and their designs. Believe me, we will just be scratching the surface, as this is an extremely broad and deep subject. Now, hopefully, you all understand that not all amplifiers are created equally, regardless of what drivel you may have heard from some of the less informed, flat earther corners of the internet. There are clear distinctions in design, including operational classes and design methodology, based on the way their output stages are configured and are built to function. But first, just what is an amplifier? Well, an amplifier is an electronic device, a machine that uses a power source that is carefully modulated by an input signal to create an output that is, ideally, a larger, more powerful, and highly faithful copy of the input or drive signal. Now, this intensified power or amplification is required to provide enough energy to set our loudspeakers' transducers, whether they use standard dynamic, dynamic compression, electromagnetic dynamic like field coils, planar magnetic, air motion transformers, or electrostatic drivers into motion. And while there are a myriad of operational classes, today we will limit our discussions only to those most commonly used for music reproduction in high-performance two-channel audio systems. Now, there are two types of audio power amplifiers available today, regardless of operational class. You'll probably recognize their names. They are the push-pull and the single-ended configuration. These terms apply to the method of operation used with the power output devices to create the final signal amplification. With the single-ended variety, one device, a tube or a transistor, or a group of similar devices working together as a single unit, is used to amplify and reproduce the entire output waveform. In the push-pull configuration, two separate devices, tubes or transistors, or groups of similar devices working together as a complementary pair, are employed, with each complement used to reconstruct only one half of the resultant output waveform. So how is it that they would manage only one half of the output waveform? All right. Picture a sine wave. Got it? Good. Now, envision a horizontal line running through that sine wave at exactly the vertical midpoint. We will now refer to that imaginary line as our null point. And we will have the top one half of the waveform, or the crests, residing above that null point, while the bottom one half of the waveform, the troughs, will reside below it. In the push-pull design, one of the two devices, or groups of devices, is responsible for reproducing that top half of the waveform, and the other, its complement, is responsible for reproducing the lower half of that waveform. In other words, one complement recreates the crests, and the other recreates the troughs. Which complement is on and which is off at any given time is determined by where the drive signal is in relationship to that null point. If the drive signal is above the null point, our imaginary line running horizontally through the full sine wave, then the push complement is in its duty cycle. If it is below our null point, then the pull complement is in its duty cycle. And looking at how the power for each half of the waveform is managed will allow us to describe its class of operation. Class B amplifiers are typified by having each of the complements responsible for only one half of the full output turn on during its duty cycle. It then turns off completely when it is done reproducing its half of the output and rests while the other complement runs through its duty cycle. When that second complement is finished and the drive signal swings back past the null point into the first complement's half of the waveform, it then switches back on again. The result is that each complement is only on when the audio drive signal requires it to be. It is completely off when not driving its half of the cycle. And this is important. We'll come back to it. In Class A amplifiers, neither half of the complement ever switches off. They are on constantly. Neither half of the push-pull complement ever shuts off nor throttles back from full current draw, even during the half of the cycle that it is at rest. This is achieved by the application of a forward bias current applied to both complements, so that even with no drive signal, each complement remains fully on. Because they have the same amount of current running through them at all times, under duty and at rest, they draw as much power at idle as they do at full volume. Now, armed with what we just found out about pure Class A and Class B operation, Class B is a logical combination of those two previous classes. With Class AB operation, each complement draws current during the entire cycle, like A. However, it is biased so that it draws considerably less current during its rest half of the cycle. This prevents it from ever switching completely off, thereby providing a much more rapid and, to our interests in creating music, more linear response when asked to take over and reproduce its portion of the duty cycle than a pure Class B device. If you were to take a close look at the resultant output waveforms from each of the three classes of operation I've just described, A, B, and AB, you would readily see why no one would consider using pure Class B amplifiers for audio applications. There is a marked distortion right in the middle, vertically, of the reproduced audio signal as the complements trade off the drive signal, and the complement that has been off switches on to carry out its duty cycle. The brief period required for turn on causes what will show up on an oscilloscope as a gross distortion in the waveform when compared to the drive signal. The resultant sound this creates is really amusical. Class AB is a much more effective method, as each device, or group of similar devices, is always slightly on. This prevents hard on and off switching, considerably smoothing out the notch or crossover distortion that we see with Class B operation. And as such, the majority of today's audio amplifiers operate in Class AB. Now, finally, with Class A operation, since the devices are completely on all the time, while they offer no switching distortion, they are the least efficient class of amplification, whether they are push-pull or single-ended designs. Now, hopefully, at this point, you have made the connection that single-ended amplifiers are, by definition, Class A amplifiers, since they cannot be run in a push-pull configuration. And there are special instances of Class A amplifiers. One immensely popular amplifier design employs special thermonic valves, 3-grid amplifying vacuum tubes called triodes, in a single-ended Class A design. Because single-ended output stages have an asymmetrical transfer function, their self-created, even-ordered harmonic distortions do not cancel out as they would with the use of a push-pull output stage. Most of the primary distortions with these tubes, and as a sidebar, with field effect transistors, or FETs, are of the second-order harmonic nature, based on their square law transfer characteristics, which tend to produce a warmer and some would argue more pleasant sound. Now, though clearly colored by objective standards, subjectively this is a sound that most of these SET amplifier hobbyists are drawn to. But using more symmetrical circuit designs like those found in a push-pull output stage results in the cancellation of most of those even-ordered harmonics, inherently negating much of those otherwise rampant distortions. There are subclasses of AB amplification also, specifically for tubes, primarily classes AB1 and AB2. Now, class AB1 may be viewed as an ultralinear or partially triode circuit, and is closer to a Class A amplifier, save that its grid is more negatively biased. And Class AB2 accepts a larger input signal than either Class AB1 or a Class A amplifier, and is even more negatively biased than the Class AB1 amplifier. However, they can be quite useful, depending on design goals. For instance, many designers feel that Class AB2 affords substantially native gains in dynamic range. They all are different. That's the point of this. Now, so far, I've been discussing what are known as linear amplifiers, electronic circuits that have an output that is proportional to the input of the device while providing additional power to the load. Further, the amplitude and phase of the output are linearly related to the amplitude and the phase of the input signal in these previous classes. And before we move on to another classification of amplifiers, there is also a Class C linear amplifier. And while Class C amplifier designs offer the highest efficiency among linear designs, they also offer the poorest linearity and are completely unsuitable for audio amplification. Now, next up are the newer switching amplifier classes. The most commonly used switching amplifier class used in audio applications is Class D. Class D is basically a nonlinear switching amplifier that uses some form of pulse width modulation to control the output devices. As such, the conduction angle of each device is no longer related directly to the input signal, but instead varies in pulse width. In Class D amplification, the active devices, transistors only here, and typically MOSFETs, no tubes, function as electronic switches instead of linear gain devices. The analog signal is converted to a stream of pulses that represents the signal by pulse width modulation, pulse density modulation, or delta sigma modulation, or some related modulation technique, to constantly switch the signal between fully on and fully off, driving the output into the transistor saturation and cutoff regions. Class D amplifiers are extremely efficient, as there is no period during a cycle where the voltage and current waveforms overlap, as current is drawn only through the transistor that is on. Now, high-quality Class D audio power amplifiers have been around for some time now, championed by folks like my friend, the late John Ulrich, co-founder of Infinity Systems with Arnie Nudell and founder of Spectron Audio. I used his astounding Spectron Musician 2 amplifier in the early 2000s. And some of the most popular Class D amplifiers today employ circuitry designed and patented by Bruno Putzis, many of which have begun to rival the sound of more traditional linear amplifiers. Now, there are several more classes of switching amplifiers beyond D, including E, F, G, I, S, T, and more. As they are not commonly used in audio applications, I'll leave it to you to explore them if you're interested. You really have no reason to, but it's fascinating to see how they work. Every class has advantages and disadvantages. With Class A designs, their simplicity is a clear strength, with some using just a single device. And because they are running at full output all the time, they exhibit no turn-on delays, have no problems with charge storage, and may offer excellent high-frequency performance and broadband tonal balance. Their disadvantages include typically higher cost per watt of output, lower overall output power, remarkably poor efficiency, most under 10% or so. They generate lots of heat, and they have reduced device lifespans. Now, with Class AB, advantages include slightly higher efficiency, as well as their native linear behavior and lower distortion levels. They typically offer higher output power than Class A, and to my ears, all else being equal, they can offer much finer delineation of microdynamic events and offer a more authentic representation of dynamic scaling overall. On the downside, they still generate a lot of heat and generally fall well short of their theoretical maximum of 50% efficiency. Class D's strengths include their remarkable efficiency, typically 90% or higher. They run exceptionally cool, and they can offer tremendously high wattage output to weight ratios. Some even may be driven directly from a digital source, as they can convert that digital signal directly to a pulse width modulation signal to drive the amplifier. And because of their inherent low frequency abilities, efficiency, and power output, Class D amps are an excellent solution for subwoofer amplification. Their disadvantages include their extreme complexity, and some listeners find them to be somewhat less natural sounding overall. Now, I hope this broad overview of audio amplifier classes and designs has afforded you a little better understanding of how amplifiers differ and why those differences may matter. But guys, regardless of class, even today's most affordable amplifiers provide a level of purity, accuracy, tonal balance broadband, and overall fidelity that simply wasn't available at virtually any cost 20 years ago. And if you push me to pick my current preferred amplifier designs based purely on their sonic accomplishments, I'd have to say that the Pushpull Class AB design would get my nod today. With that, I'd like to offer my sincere thanks for taking time to drop by and visit today. Remember to subscribe and to like and share your favorite episodes, as well as to post your comments and questions. Please stay safe out there and keep the music playing. Till next time, cheers.